of being differentiable. The idea of whether or not the slope is continuous, not just the points being continuous, but the slope itself. We've already talked about what it means for the points to be continuous, but how can you talk about the slope being continuous? So visually, there are like 3 quick things you can look for to just look at a graph and say, yes, it's differentiable, no, it's not. Similar to how you could look at a graph and see if it was continuous or not, if there was any brokenness in the graph. So visually, you might look to identify a corner, okay, or a hard corner. Okay, classic example of that is the absolute value. It's Latin. It means example. I'll just change it to EX. IE is like in other words, but it's also Latin for in other words. So, I don't know. Mr. Bexer's not here anymore. He was our resident Latin. He took Latin and that was his language. Like he didn't take Spanish 1, 2, 3, took Latin 1, 2, 3 at his high school. So, anyway, I don't remember what it stands for. Okay, so a corner. If you have a corner, that means the slope is not continuous because the slope abruptly changes from one value to another. There's no graduation, no gradual change. It's an abruptness, and so that's non-differentiable. Okay, another one would be a cusp. Okay, cusp looks like this. All right, the corner is where it abruptly changes from one numerical value to another numerical value. A cusp is where it changes from one type of infinity to another type of infinity. So on a cusp on one side, it's going to be approaching a steep slope of positive infinity, whereas on the other side, it's decreasing at a steep slope of negative infinity, or vice versa. A cusp could go the other way, like that. Okay, so it's the changing of the slope. It's not a continual, it's an abruptness. Okay, and the last one, which is a visual cue, is a vertical tangent. Okay, an example of that would be a cube root. Because a cube root has a vertical, although it's a continuous function, it has a spot where it has a slope of infinity. And that happens right at the origin, right here, where the slope is so steep that the tangent line would have a slope of infinity. Okay, infinite slope. And that's going to be true for any odd root. Cube root is just an example, but it could be a 5th root or a 7th root, or any odd root would be an example of a place that would have a vertical tangent. So that's visually. Proving it is a little bit different story. It involves some limits. So proving differentiability. You were playing around with it last night. You weren't doing a ton of proofs, but you were just talking about, all right, what about on the left? What about on the right? Okay, what's going on? So first, when you want to prove differentiability, it's sort of like a checkbox. You got to prove continuity first. If it's not continuous, it's not possible to be differentiable. So you have an open and shut case right there. So prove continuity first. And so you'll prove that the limit of x approaching a from the left of the function is equal to the limit approaching a from the right of the function. And then you'll prove that that's equal to f of a itself, and you have a nice little happy continuity proof where all three requirements of continuity are satisfied, where they're all equal. If you can't prove that, then it's not possible to prove differentiability. So if you pass the first level, you pass the first test, so we'll put a check in our checkbox there. Okay, we've proved continuity. Then we can move on to check the one-sided derivatives. And checking one-sided derivatives looks similar to a continuity, where you're doing a limit as x approaches a from the left, but it's of f prime. And it only requires the two sides. It doesn't require the value of the derivative itself. So there is no third part to that. It's just checking the two one-sided derivatives and showing explicitly that the values of those two things are equal. And then you've proven continuity and differentiability. And so I'm going to do a very, very basic introductory example with you. Okay. All right. So something like this. Explore the differentiability of f of x equals the absolute value of x squared. Okay, the absolute value of x squared. All right, so first, you want to do your continuity check. Clearly, the point, or maybe it's not clear, but our continuity check is going to happen at the value a. Because in an absolute value, that vertex is where we need to check it out. And so we'll check the three pieces. This should go pretty quickly. We've got the limit as x approaches a from the left, the limit approaching a from the right, and f of, let's see, those should be zeros. 0 from the left, 0 from the right, and 0 itself. So we just check those three things. And we want to check that those all three are equal. So for sure, if we plug in 0 from the left, we're plugging in a negative number, but we square it, and it becomes absolute value, so 0. We plug in 0 from the right, we square it, we get a positive number, and then we plug in 0, and we get 0. So our continuity check is good. Okay, now, our differentiability check. In order to check an absolute value, you have to write it as a piecewise function. Okay. F of x. Okay, so first we want to think about what is this function like if I define it as a piecewise function. All right, so the absolute value of x squared. When it's positive, do I even need the absolute values at all? Okay, it's positive, I square it, it's positive, I've still got it. Okay. What about when it's negative? Do I need the absolute values when it's negative? Okay, well, if I plug a negative number in, what happens first, the absolute value or the square? Okay, and the square makes it positive, therefore I don't need the absolute values anymore. So all of a sudden now, if I'm checking both sides, it becomes irrelevant. And I don't need the absolute value anymore. Okay, so my derivative for x greater than 0 and x less than 0 is 2x for both of them. So then I check the differentiability. So a approaching 0 from the left and a approaching 0 from the right, but I'm doing it into my derivative now. So if I plug a negative number into my derivative, I'm going to get 2 times a negative number, which is going to be negative. If I plug 0 into the positive one, I get positive. Okay, I'm going to pause the recording. All right, so coming back to our differentiability, we showed that the left derivative is approaching 0 and the right derivative is approaching 0. There is no abrupt change there between the two because negative 0 and positive 0 just on either side of 0. Therefore, this is proved to be differentiable because these two things, 0 minus and 0 plus, are considered the same number. They're both approaching 0. And so we say the overall limit as x approaches 0 of the derivative from either side is going to be 0. Those two things are equal. Therefore, we've now proven differentiability. So here's an example. Don't just assume that an absolute value is non-differentiable. This was an example of an absolute value that ended up to be differentiable because it had a square on the inside.